Okay, so just to rehearse what we've done, ladies and gentlemen, we added a new model. We added a person, and from the palette items here, the pictures, we added a person to them. Then we created one called city. Okay, an agent called city, and for the agent city, we went to this and dragged in a rectangle. The rectangle was located at 50, its upper left was at minus 50, with the 100, height 100. So it extends here 100 and 100 up there. Okay, ladies and gentlemen, what we now did was we dragged in city into main to create a population of cities. We added a parameter called count cities, and this parameter is an int, and its default value will be 10. And cities will have an initial number of agents of count cities. Okay? Okay. Now, for initial location, ladies and gentlemen, I would like you to place this agent at a specified point, and we're going to say here uniform from 0 to this dot space width. We've seen this before, and this 0 uniform space height. Do I need a semicolon after this? No, I don't, because it just wants a value. It's not looking for me, not telling it do something. I'm just telling for x, the value is, to compute the value, use this formula, this so-called expression. Same thing with this. Okay? Are we okay with that? Build early, build often. Okay? Great. Okay? Population of cities. So let's run it and see what happens. Okay? We haven't yet added population of people. That's notable. Okay, here are our cities. All right? Okay. If we want to, ladies and gentlemen, if we want every time we run it to have a different layout of cities, where would we go? Anyone remember? Where would we go? Okay, but if we want to have a different if we wanted every time to have a totally different random depiction, we'd actually need to set this to use a random seed. So to do that, that's on a per experiment basis. It's not like the whole model has a random seed or fixed seed. It's a per experiment. So go to the experiment and set it to be a random seed. Is that okay? Okay. So if I run that again, I will see a different layout of cities. Yet again, I could actually just stop it here. Yet a different layout of cities, a different layout yet, and yet a different one. Okay, great. Ladies and gentlemen, we want to have these cities be placed in a distance-based network with a distance threshold of 200. Actually, sorry, make it a distance threshold of 500. Okay. So here are these cities. How would we do that? How would we place them in a network with a distance-based network? Who would be responsible for this? With this model, it's especially important to be clear about who's doing what. They'd be placed, what is it that would impose a network on cities? The characteristics of that network. Where do the cities live? In what? In Maine. So we'll go to Maine. That's what the city population lives in Maine. So we're going to go to Maine, and we want to put in a network type that's distance-based with a connection range of 500. Okay. Connection range of 500. That's in main. Scroll down to this properties for main. Scroll down to space and networks. Network type distance-based connection range 500. Now, if I run this model, will I see the network? What do I need to do? Yeah, I need to go to city, and I need to go to connections, and what do I need to do?
Select the agent.
So I'll need to go to connections, and then what?
Animation.
Animation, draw a line connecting agents. All right? Okay, can we see this now? Let's go run it, right? Run. Okay, there we go. So now we have lines going between cities, okay? Okay, great. Now, by the way, there's some other GIS examples where we actually load in city information from GIS and situate these cities in space, and then you have the roads between them. So this is not combined with GIS. It could be very readily and very powerfully, but I'm showing it at a more abstract level. Okay, so we have these connections between cities. Okay, now, ladies and gentlemen, now we're going to take a different turn. Now let's go to city, and we're going to drag in a population, ladies and gentlemen, of people. So this will be called population. And now, ladies and gentlemen, I would like to set there to be a population size. Now, where would this parameter go? Suppose cities differ in their population. Where will population size go? In city. So each city is going to have a population size. And what sort of parameter will it be? Will it be double or int or what? Int indeed. Now, its default value, if nothing else is specified, I'm going to say that it's drawn with a certain distribution. Maybe it's log normally distributed, log normal, maybe with a log mean of, I don't know, 2 and a log standard deviation of 3 and a minimum value of 2. That's a bit small. Make it 3, 4. I don't want to make them huge cities, but I'm just gonna have some variability for cities. So some are going to have lots more people than others. Okay? Cities is probably its municipalities or towns. Okay? Okay, this is going to be log normal. Now, log normal returns returns a double precision value. So we're going to need to turn it into an integer. So we'll do what's called casting it to an integer. We'll coerce it to an integer is another way we say this. We turn it into an integer. Now, by the way, does anyone remember, if I wanted to get a sense of how big this is, 3, 5, what could I do? I could go up to this, right? And I could go to log normal. Hey, where are you? Where art thou? Hello? Hello? Really? Anybody home? Okay. Kurt, do you see that? Okay.
Mine works.
Okay. Mumble.
Mine works.
Okay. Well. Okay. Ladies and gentlemen, so we're going to set this population size to differ by that, and this population, this int basically means this returns a value like, 32.6, and it will turn into a 32. Or this will return a value like 235.35, and it will turn into 235. by casting it to an int means we truncate it as an integer. Okay? That's what that does. And we'll make that the size of this population of agents. So this will be population size. Okay? Population size, number of agents. Mind you, that will be the population of that city. Are we okay with that? Okay, ladies and gentlemen, the plot is going to thicken. Okay, let's run this model. Oh, by the way, let's go up to Maine. Let's go down Maine, and let's look at cities. Population size. Where did this come from? From whence did this come? Anyone remember? Who created that? You did. Just 2 minutes ago, right? So this is just the default value. If you don't say something different, this is what's going to be used. Now this is an expression, right? It's not one value. It's the expression that will be used here. So we put that in by convenience, and we're not going to change it. That's fine. But later we could come back and change it. An interesting question is, would this work here? No. Okay. 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 Mumble. Okay.
Does it close that window and try again?
Can you close any logic? Open it.
No, just that window.
Which window?
The distribution window.
Oh, I did.
Oh.
Yeah. No. Keep on closing it and reopening it. Yeah. It's not a happy camper. Okay. I bet if I closed any logic and opened it again, it would be fine. That's the truth of the matter. Okay, there we are. Okay, and let's go down and look at these cities. City 1, population size 0. Oh my gosh. City 1, population size 0. Population size 53, 27, 28, B8, 115. We have a bunch of underpopulated cities, including some with 0. Okay, let's go frob that expression. Okay, let's adjust that expression. Okay. Okay, so ladies and gentlemen, in Maine, for the cities, we're going to bump this up to 5 and 5. It would be nice if I could do this thing. Look at that, Kurt. It's still doing that. I'm going to leave any logic and come back in. I bet it will fix it. One thing I will tell you is if you're using GIS, our group has noticed that there is, after a couple hours of using GIS, maybe even after an hour, any logic will tend to get slower, and if you leave it and you come back in, often you're fine. But there's some sort of memory leak where its memory will start to be chewed up over time. I have noticed that, and to the best of my knowledge, it's not a problem with anything serious, but it is something that affects how slow it is. Okay, so here we're coming in. Okay, it's loading this in. Here we go. Back again. Okay, let's go check it out. Okay, so I'm going to go here, and I'm going to try to insert this thing here. There we are, a thing of beauty. Okay, good. So I'm going to do log normal. Boom. And unfortunately, it doesn't have a very good scale here for what these scales represent. So 3, okay, mu, sigma, okay, minimum value 3. Okay, minimum value of 0. Okay. Maybe I'll make its minimum 1, and mu will be 5, and sigma will also be 5. Okay. Somehow that doesn't look that great. Let's give that a try. Okay. So 5, 5, 1. I don't want it to have 0. Okay. 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 Now it's struggling. Probably means some of the cities are going to have a very large population. Okay. Come on. Yeah. It's using a lot of memory. Okay. I probably overdid it. Okay. Oh, look at that. Out of memory. Okay, you may encounter that. We might as well discuss it. Maximum available memory. You can actually allocate this larger. I'm going to make it 4 times as large. Let's try that. Now, probably it's still going to be larger than we want to deal with. And for those who are using PLE, it's probably not going to be feasible. Okay, so let's try this. Okay. Now it's allocating this. Okay, there it is. Let's go see our population sizes. Cities. Okay, here's city 1, 2,974 people. This next is 200,000 people. The next is 53, 219, 43,000. Okay, another 48, 52,005. Okay, it's a little bit too variable. I don't want to be dealing with things that are like hundreds of thousands. So I'm going to be lowering that a bit because I'm going to be packing them in there with networks. Okay. Sure, I'll make it 531 or 532. Okay, 532. Good. There we go. Minimum value 2, mu is 5, sigma is 3. Okay, here we go. Let's go down to cities. Okay, 4496, 83,000, 418, 821. Okay, we can deal with that. 4, 626. Okay, 27,000. Great. Okay, ladies and gentlemen. Next, what we're going to do is we're going to go and for these cities, this is a little bit too variable. I'm sorry, I'm going to have to ask your indulgence just to avoid causing a lot of slow performance. I'm going to put in a uniform distribution between 100 and 500. I'm sorry, it's just, I do want this performance-wise to be okay when imposing a network, and I haven't done it with that high uncertainty before. Okay, so 0 between 100 and 500. Okay, we could do the log normal later. Okay, fine. There we go. Okay, so in short, cities is going to have this as the distribution, 100 and 500. Okay, ladies and gentlemen, next I want to get to simulating what's going on in a city. Okay, within a city, we are going to lay people out in a environment as well. So who's going to establish, for cities, Maine established the nature of the environment. It established the network they were in. Who's going to do it for the people within a city? The city, indeed. So let's go to the city, and let's go down, and you'll notice it says select the agents you want to place into the environment. And we're going to define a distance-based network with a connection range of, we'll say, 5. Okay? Within the scope of that city. Okay? And now, what do we have to do for that network to show up visually? Yeah, connections in person. And what do we have to do? Draw a line connecting agents, right? Now, we could use a different color here. We could use a red color for those lines, for example, to make it obvious they're within a city lines. Now, there's one more thing we have to do, though. One more thing. Within a city, ladies and gentlemen, what else do we need to do to provide the person to be placed in a network based on their distance? What do we have to do? We have to distribute them according to their what? To their location, right? Okay, so ladies and gentlemen, the way I'm going to do this is I'd like you to go to city, and I'd like you to scroll down, and I'd like you, for the space and networks, here, I'd like you to go place a layout type to be random. Okay? So they're going to be a distance-based network, but they're going to be randomly located within the city. Is that okay? Okay. Here we go. So let's run it. Oh my gosh! Okay, that's not what I was expecting, but
That's all the cities superimposed on each other.
Indeed.
You probably have to go to the shape and say, don't show it on the top surface.
Well, okay, so here are the cities, and the problem is they're not limited to this little box. They're being spread out in space, and so they're being, indeed, this is the superimposition of these guys. But actually, I do want them to show here. It's just I want them confined to that little box. All right? And that ain't happening. But you notice it's because we say the width is 500 and the height is 500. Does anyone remember how big this box was?
100.
It's 100 by 100.
It's not.
Mm-hmm.
It's centered.
Yes, it is, but I believe it's going to place them in that upper left. So let's go to the relative to the upper left. Let's go do this. City, we're going to set the width to be 100 and height to be 100 for the space dimensions. We'll see. This ain't a chemistry lab.
I'll bet you supper that it's going to be in the bottom corner of the square.
I'm not a betting man. There we are. Okay. So now we've got it close, but this ain't a game of horseshoes. So what are we going to do? Let's draw this over like this. Okay? Okay. Yeah. So ladies and gentlemen, we're going to draw the city so that its rectangle begins up here. Okay? Okay, I'm sorry. This is going to cause some trouble. This actually will correct that problem, but it might cause other problems. If we watch, now it'll look fine like this. They're located within the city more or less. But I think it may cause some other problems. So give me just a second to evaluate this other solution, which I think may work. So pardon me for just a sec while I confirm another option, and then we'll be hunky-dory. Okay, I'm just going to say user defined here, and what I'm going to check here is if we could do the following. Okay, here we go. Ladies and gentlemen, uniform minus 50 to 50, and same thing for this guy here. Let me just try this and see if it works. Yes, that's how we want to do it, ladies and gentlemen. That is how we want to do it. Okay, Kurt? Okay, ladies and gentlemen. So we want to we want to get a population, and population within city, and we want to set it to be in the specified point, minus 50 to plus 50, minus 50 to plus 50. The other thing we want to do is for city, we want to go down and make it to have a layout type user defined. Okay? Okay. So I'd like to emphasize this, particularly for the people who are out of the room. If you go to city, go down and make the layout type user defined. Okay? In city, go to the space and network properties and go layout type user defined. Okay? Okay? And ladies and gentlemen, then we're going to go, so city, space and network, make it user defined layout, and then for the population, make it in the specified point. This is the population in city, in the specified point between minus 50 to plus 50. Minus 50 to plus 50. Now, the reason that would be nice is the fact that the roads will connect cities at the correct point, at the center point, which is desirable, rather than having it connect to the upper left. Okay. Are you doing okay? You folks hanging in there? Okay. Yes.
So go back to this, jump back. Just show the cities in the main.
The downside is that these cities.
Okay, yep, cities in Maine.
Just show the properties again.
Sure. Cities in Maine. And the properties for these, I set it to be, initial location is here. Yeah. Okay. And then, and that's the initial location, yeah. Okay? So that's just the cities in Maine, they're located here.
I think you already did that.
Yeah, the capitalization in space width is for the W, for the width. The same thing for the height, the H. Okay, so if we run this, this is what we'll see, which makes up for an enthusiasm what it loses in beauty. Okay? Makes up for insignificance. So here's city 1, here's city 2, here's city 3, and they're pretty packed in there.
Could you reduce the size of that?
Reduce the size of the people. Yeah, let's do that. Okay? How are we to reduce the size of this? Partly it's to show you how you do that. Okay, go here, and let's set the scale for the person to be smaller. You'll notice that first of all, we could do it this way. We could do it, we could try, okay. Uh-oh. Hey, oh man, okay, oh man, okay, he's exhibiting truculence. But there's a better way to do it. Well, there's a programmatic way to do it. Gosh, this guy is like become, okay, there he is. Okay, let's make the scale for him 0.1. What do you think? 0.1 scaled in X, Y, and Z. Z. Okay? Okay. Okay, what's that? Those are networks, ladies and gentlemen.
That's okay, so what you're doing is you're going, they look like bacterial dishes.
Yeah. I know, I happen to think it's pretty neat, but,
You just clicked on, it went into, oh, that's interesting.
yeah. Okay, ladies and gentlemen. Okay. So, we have very small people, right? Okay, so let's increase the network distance range for people a little bit. If you go to city, where would we set the range by which people within a city are connected? From 5 to 10. How do we do that?
What did you change the scale to? The
Point,
vertical scale?
0.1. But I think that methinks that was a bit small.
Both for X and Y?
And Z.
Yeah.
Yeah.
All you do is you just
Okay.
scale that.
Okay, let's make it, maybe we'll reduce it by 0.25
4.25 for all three of them.
so they won't look like bacteria. Okay, okay, so let's get a person and
Oh,
0.25. Okay? Okay? Okay. And now let's run it and see what it looks like. Okay, now you can actually see some anthropomorphic characteristics, if not all the shapes of each visage. Okay, so now let's set, how are we going to set the connection range for those people to go from 5 to 10? Whither will we go? So okay, in city, yep, so we're in city, and where do we go in city? We go to space and networks, and we're going to change it to 10. Okay, so I went to city, I went to space and networks, and I changed it to 10. Are we okay with that? Okay.
Oh, this is a name.
Ladies and gentlemen. Okay. Okay. So let's go do this. Okay, now we're talking. Now we're cooking with gas. Do you see something like this? Yeah, okay. Okay, ladies and gentlemen, now we're going to see some interesting things. Now that we have people having some shapes, we're going to start to see them engage in behavior. Okay? Do you think they could be a little bit larger? Yeah. Maybe we can make them, do you want to try 0.5? Would they look what? Too big?
No, they look okay.
Okay, 0.5. Okay, let's try that. Good? Let's try 0.5. There we go. Okay, yeah, they don't look too bad. A little bit dense at places. Kurt, 0.5. 0.5 it is. Okay, so we're going to keep it at 0.5. Okay, ladies and gentlemen, now let's add some behavior for these people. Okay, I'm going to first do the unique thing you haven't seen before. Ready? Here we go. Okay, I'm going to add in to a person a state chart that's going to be called mobility state chart. And we're going to have a state that's going to be I don't think we need a state chart. I think we could do it with an event. So I'm going to eliminate this state chart. Okay? Let's do it with an event. We'll add an event to a person that periodically is going to cause them to leave, to migrate. This is going to be migration event. Okay? Migration event. And this is going to be a rate of 0.1 per year. Okay? And when they leave, ladies and gentlemen, they are going to go from their city to another city. What do you think of that idea? Are we okay with that? Okay, so, ladies and gentlemen, first we're going to find a city to which they head. And then we're going to place them in the city, have them go to that city, okay?
Just a quick question, is the model time in hours?
Sorry?
Is the model times in hours?
Okay, that's a good question. The model time is in
Years.
years.
Or years, okay.
Years. By the way, it wouldn't be a problem per se if, parts of the model are running with hours and parts with years. It would just, it'll just be certain events will tend to often occur rarely compared to others. But there's nothing inherently problematic about it. It's just that you want to be conscious of that, and you don't want your model to run so slowly because there's all these things going on at the level of seconds. You very rarely see the things at the level of years unless you have to. Okay, so ladies and gentlemen, I'm going to pick a random city and have them go to that city, okay? So this is going to be, when they move, okay, I'm going to have them, I'm going to say city, destination, city, just give it a nice name, equals, and I want to find out what's the name, or I want to find out, I want to pick a city, okay? And let's suppose, for simplicity right now, we pick it randomly. It wouldn't be that hard to make it pick it according, with the probability according to its population. We could do that. And I'd be glad to do that if there were interest in a few minutes. But I want to get to the essence of it right now. So I want to pick a random city for the moment, okay? How am I going to do that? Where are the cities living? The list of cities. In what? In Maine, right? I can actually say Maine.cities, ladies and gentlemen, here. And then, does anyone remember how I get a random one from there? I actually say a random one, like that. Is that okay? Okay. Now, ladies and gentlemen, we are going to do the following. Who is this? This is occurring in the context of a person. Who is this? Who is that referring to? It refers indeed to the person. This dot go to population, and I'm going to say go to the destination city dot population. I want to move to a destination city's population. And then what has to happen? If I'm going to get transmission of infection on that network in the city, what has to happen? What do you have to do to nip me into the network? Apply network, indeed. Destination city dot apply network. Boom. Okay?
Is there a move to population?
That is move to population, go to population.
There isn't a move to? They just transport some?
They transport, yeah. To the best of my knowledge, I don't think there's a move to population. No, they teleport. Okay, now, by the way, we could have this just go to cities that are neighbors of my city, like the direct neighbors of my city. That would be an interesting one. So one thing I could do, this would be an interesting thing. Watch this. City dot random. Okay, I thought there was a random neighbor. There is a message delivery type.
You're not connected? Are they connected?
Yes, they are. The cities are connected. Get random connected agent. So here I could actually have it move to a neighboring city. an immediately neighboring city if I wanted to do so. And then that will use the city network. You know, maybe these roads or rail connections are actually links between farms in terms of sharing animals or something like that. So maybe that network of farms, maybe cities correspond to farms and farms share animals with other farms, something like that. And in which case this would make sense. You go to one of the farms that is affiliated with your farm or something like that. Okay, ladies and gentlemen. Okay, it's an unhappy camper. Okay, cannot convert from agent to city. Okay, this is a good thing to know about. So there are some functions in AnyLogic that are very generic. Get random connected agent. It returns some agent, a reference to an agent. I need to say, hey, look, this region is a city. I know cities are only connected with other cities, so I know it's a city. Any city is an agent, but I know this is getting a city because cities are only in a network with cities. So I'm going to cast it. This is saying, hey, turn it into a city. Just treat it as a city because I know it's only connected with cities. AnyLogic got rid of most of that in AnyLogic 7 with generics, but it's not entirely. Okay, let me put this up on the board. This is in migration event, which goes off 0.1 hazard rate per year. So we're finding a random city, which is a neighbor of our city. This person is going to the population of that city, and then we tell that city, hey, go recompute your network. Does that make sense? Okay. Okay, who needs Gregorian help? Anyone need Kurt help? Okay. Okay. You got it?
Yeah.
Okay. Okay. Good to get them all. Yeah. Okay, yeah, capitalization will do it.
That's the same. Yeah.
Okay. Anyone else need help? Yeah.
What term of my individuals are connected with my network? Which was a step way back.
Okay, so these are within a city?
Yes.
Okay, so within a city, you're going to want to check a couple things. You're going to want to check within a city if the city itself should have a space and network area where it should specify the network type as distance-based in a connection range of 10. But then you will also want to check that the person's connections are set to draw a line connecting agents is checked, and I made it a red line. So there may be a network there, it's just not showing. Yeah, you might want to make it red because it'll make the distinction clear. Okay, so ladies and gentlemen, do you see what I'm seeing? What's going on? What's going on? Oh. Uh-oh. Oh. Oh my. Oh my. Okay. Okay, that's interesting. Okay. Yeah. Okay. Okay. So moving right along. Okay. So.
That's where exactly your population is going.
I'm going to teach you a bit of debugging now. So, yeah, so, okay, ladies and gentlemen, apply some principles. Don't panic, and, don't flail. Form hypotheses, investigate them, test them. Okay, so I'm going to create a separate copy of the model for debugging. I'm going to create a debugging version of my model so I can go at it with abandon if necessary. Okay, so I have hypotheses. One hypothesis, they're going to some other city population, or going into somehow into La La Land, which, I admit I lack a clear, crisp technical definition of. But let's get a person. Let's go see where they are going to. Where do they think they're going to? Let's go add a trace LN here. Here we are. Trace destination city, and I'm going to have it print out the name of the destination city. So I'm going to here. Okay, let's go watch where they think they're going, to whence they think they're going. Okay, watch this. Okay, and now let's go look at console. Okay, they think they're going to each of the cities. That's not bad. Okay, what happens if I... Wait a minute.
I bet you they're landing on top of each other.
Okay, so let's... Okay, so that's what I'm wondering. Okay, let's go see. So watch this. Watch this. Population. Okay, are you ready? Watch. So I'm going to say, okay, which before the move has a population of, and we're going to say destination city dot population dot size before the move, okay, and then I'm going to say trace LN. So destination city has a population of after the move. Okay? I'm going to go see, does its population actually go up of the destination? Right? So one hypothesis, they're actually going there, but they are just not being clearly shown or this as such. Okay, here we go. And another hypothesis, they're going to La La Land. Okay, here we go. So I'm going to root city, which is 330, and now it is 331, 261, 262. Okay, Krugerian hypotheses are seeming ascendant. Okay, so let's go now. Maybe they're landing at that place in a different shape. So we can investigate this in a couple ways. I could change their color so they'd be very obvious when they land there. I could change their size. That would be interesting. So it's very visually obvious where they land. I could check their location after they land there, and see what their location is. So I could do any one of those, and I'm wondering what is their X and Y location after landing. Okay, so one possibility is they're landing on top of each other. Another possibility is they're landing outside the area. Yeah, Tiffany.
So if we reset their network connection, why would we reset the layout?
It's a great question. It's a great question, because generally that would scramble, not necessarily, I'm not actually clear what that would do. The reason I don't think it's necessary is because the population within this is laid out using this sort of way in a specified point. And normally when you add someone to this population, they are laid out with an X and Y location that uses these. But I'm wondering, that's one of my theories, that maybe they're not being laid out properly. I would be cautious to say apply layout, because I think it might scramble everyone in there already. I'm not sure about that, but we could check their locations when they move.
The layout is user defined, right? So
I know it may not, if it was random, it would scramble it all.
yeah.
But if it's user defined, it might not. It probably wouldn't. But let me go see. Okay, so we verified they're reaching their destination. They're simply not being displayed in some way, or they're being displayed atop of others. So one hypothesis I have, they're being displayed off the screen. They're landing there, and their visual display is just off the what we're looking at. Another idea is they're landing on top of someone, and I think that is more likely, that they're all landing at a certain location. So, ladies and gentlemen, let's go see what their X and Y location is, shall we? After the move. So, I'm going to say so I might as well say this is currently at X, is currently at this dot get X plus this dot get Y plus and is going to, okay, and now I can reuse this down here. So so I'll say after move, this is at, and I'll ask what's my location now in destination city. Okay, in destination city, which now has a population of after the move. There we go. Thing of beauty. Some of us actually like debugging. Okay, so watch this. Console. Okay, check it out. Here we go. Oh, look at that. Looky that. Do you see what's going on? The fox has shown its tail, ladies and gentlemen. Huli Weba.
For those of us that speak Chinese.
Huli de Weba. Okay, so they're at this location before, and where are they afterwards? At 0, 0. Okay, ladies and gentlemen, we have the culprit. We just have to assign them a location in that new destination. Are we ready? Are we ready? Okay, ladies and gentlemen, I'm going to do it. Time is short, and I'm going to do it in a way that makes me uncomfortable. But it'll work. Okay. It makes me deeply uncomfortable. Makes me uncomfortable. Okay, in main, I'm going to find two parameters. This will make me less uncomfortable. One will be city. This will be person X min and person X max. So these are going to be the minimum X and Y, minimum and maximum X locations. The minimum is going to be minus 50. In fact, I'm tempted to say person X min within city. Okay, minus 50. and X max within city. Okay, let's get that down there. Person X max within city, and this is going to be a max of 50. Okay. Okay. Next, I'm going to paste. Okay, and these will be person Y min within city minus 50, person Y max within city, which is going to be plus 50. That's it. Okay. Okay, now we're cooking. Okay, now in the city, ladies and gentlemen, we're going to do, instead of uniform from minus 50 to plus 50, what are we going to do? We're going to do it from main dot what we call it, X, no, what do we call it? The person X min within city, person X min within city, and person X max within city. Boom. Okay, then I don't have to hard code these things. Same thing with these, Y. Main dot person Y min within city, because if you leave your code with these numbers scattered around it, you might update X min, this should be min, X min, and X max. If you leave your code with these sort of numbers scattered around it, you forget to update it in one place, you update it at others, and the model breaks. So what did I do? I added to main person X min within city, person X max, minus 50 plus 50. And same thing, okay, I had a default, yeah. Minus 50 plus 50, minus 50 plus 50. And then within city, I use those to determine their initial location. And
Should that second one be max? Yeah. X-axis?
oh, yeah, this should be max, sorry. Yeah, thank you. Okay, okay, we're in good shape. And similarly, where else do these get used? When they move to that new city, they get moved there. So we're going to do person, or sorry, we're going to use this dot set xy. The x value is going to be drawn from that, and the y value will be drawn from the corresponding ones as well. Okay?
You have to add it to the city's location?
Sorry? Just, it's the person's location within the city? No, it's just relative. There we are. Okay, this dot set xy, this is their x location. It's just the same expression we had in city when we set it for the population. The same thing here, we're just replicating it down in here.
Make that bigger.
Yeah, I'll make it for the big screen. Okay. Okay, you don't have to copy this trace ln stuff. This was just for debugging. This is just for debugging. Now in this case, I actually haven't done anything destructive on this model. So I can actually copy this back to be my main model. That's good. Okay. I actually didn't need to destroy anything. So you can cut these out. Boom. And cut this out. Boom.
Is that second uniform indented?
No, it's like it's indented here to align with the first one. This is good sort of style to show it, sort of to be able to clearly say, okay, this is the first argument and this is the second argument. You kind of line them up visually. Okay, does anyone need a bit more time with that?
Make that bigger.
Sorry?
You make that begin.
Yeah. Here, I mean, I can align it here. It somehow got twisted. Here.
The size of the tab, I think.
Yeah. Yeah. It's amazing. In 2016, they still haven't figured out how to standardize those things.
They don't have even standardized end-of-line characters between things.
Yeah. Okay. So this was the same as before. Oops. Basically, everything was the same as before, except this was added, set x, y. Are we okay with that? Are we okay? This is the same formula that's used exactly in the population for city. And this is the same formula as well. Same expression used to determine the y and the x within city. Are we okay? We okay with that? Okay, ladies and gentlemen, let's go debug this, or let's go run this thing. Ready? Okay, new networks are formed. Network ties are broken. People move. People shift. They shift to neighboring cities. Okay. Okay, ladies and gentlemen. Now, if I may be so bold, I would like to suggest the following. I would like to suggest in our final minutes of the day, I think we can do it. I would like to add an SIR state chart and have infection spread. So then people who move will bring infection from one city to another. What do you think? Okay? So, ladies and gentlemen, we've done it before. We can do it again. It's not very hard. Okay, let us go add in an option list, right, for messages. We'll keep it a very simple model this time. The message will be the message exposed. We won't even have a separate force infection message. Sure, we'll have a force infection message, just a force infection. Okay. In main, we will add a parameter, which will be duration of immunity. Excuse me. Duration of immunity. What sort of parameter will this be? Time parameter indeed. We will add a parameter that will be duration of infectiousness. What sort of parameter? Time indeed. It'll be measured in days. This other one will be measured in days as well by default. Duration of immunity in days by default will be 270 days. Duration of infectiousness in days will be 7 days. Contact rate in main will be how long? What sort of parameter? We could do it as a double, but it's even better to do as a what? A rate, contact rate. And this will be a per day contact rate. It'll be 1 per day. There will be a incubation period or latency period. Latency period. And that will be what sort of parameter? Time parameter. And it'll be measured in days, and it will be 3 days. Okay? Okay? Are we okay? Okay, ladies and gentlemen, and whoa, one more parameter, which will be transmission probability. That will be a Boolean, a tuple, with a value of 0.25. Okay? Okay. Yeah. Great. Great. Actually, make it 0.5. 0.5. Okay, excellent. Measles has a quite high transmission rate, actually. Okay, 0.5 transmission probability, okay? Are we okay with that? Okay, having done that, let's go through them. Duration of immunity is a time parameter, 270 days by default. Duration of infectiousness, a time parameter, 7 days by default. Make sure it's not seconds, yeah? A contact rate, 1 per day by default. A latency period, 3 days by default. So contact rate is a rate parameter. Transmission probability 0.5. Are we okay? Okay, now let's get a person. We can quickly build the state chart. Okay, ladies and gentlemen, we have the pieces that we need. We have the network. We have the parameters. You have the ability. Let's do it. Okay, so state chart entry point. Infection state chart. Infection state chart. Boom. Okay, what are the states going to be? Susceptible, exposed. Next, infective. Next, recovered. Okay, what transitions do we need? Susceptible to exposed for sure. Next, exposed to infective for sure. Next, infective to recovered. Make sure these are connected on both sides. And finally, recovered to what? We have a waning immunity time. What do we need? Back to susceptible. Okay, ladies and gentlemen. Okay. Okay, here we go. Okay. Okay, ladies and gentlemen. Now, I'm going to argue we actually need 2 transitions here for my plans between susceptible. Oh, what are we forgetting? What are we forgetting between susceptible and exposed? One transition will go directly. Which one will that be? What sort of transition will it be? There'll be a message transition. In which message? To go directly? We have a probability of transmission given discordant contact. So what does that imply? It's only probabilistic. So normally when we deal with that situation, to make sure someone's infected up first, what do? We send a what message? Force infection message. And remember, we created one, not 15 minutes hence in the option list, did we not? Remember that? Messages dot, it's exhibiting truculence. Force infection, indeed. So we want messages dot force infection. That's the particular message associated with that will bring someone directly. If we want to simulate probabilistic transmission that's not certain, but contingent on circumstance or chance, perhaps an agent's immune system status, where do we have to render that? Through what mechanisms will we use? How do we deal with a probabilistic transmission process? How can we represent that? Using a what? A branch, indeed. So we'll place a branch there. This branch will have a conditional, so by default, it will go back to the susceptible state. But, ladies and gentlemen, under what transition will it actually go on to exposed? Does anyone remember? Under what condition? What would the formula be here? You've done it before. It begins with an R. It has a big F in it. It ends with an M.
Red. Hey, could you just do that in a guard instead of a branch?
No. No, a guard doesn't change.
But shouldn't it check every single time that a message is sent?
No, it doesn't. You can double check that, but I'm pretty sure the answer is no.
Right.
Yeah. Random from, or sorry, random from, what am I saying? Random true. Sorry, I'm out to lunch. Random true, and what is this going to be based on? We're flipping a coin. What's the, on what will the coin be based? This is based, what is this one here, ladies and gentlemen? Just to be sure we're all on the same page. This transition here from susceptible to the branch, what is that triggered by? I'll call it an exposure transition. What is it triggered by? What is it triggered? A message. Which message? No. The force infection brings them definitely to this state. The point of it is to sidestep the uncertainty. What is this one based on? Exposed. Exposed. It's based on a sort of normal exposure. We're not forcing someone initially to be infected. It's based on exposed. Okay, messages that are exposed. This one is the default, so this is uninfected, basically. This one here, and this guy here is exposed. Exposure. Okay, so this one is uninfected, or not, yeah. Okay, this infection, this is based on random true of what? We added the parameter less than 10 minutes ago. Transmission probability. That's what it's based on. With a certain transmission probability, it's flipping a coin, a weighted coin. With this transmission probability, it yields heads up. With a certain probability, the loony shows its beak. Or the eagle, its claws. Okay? So, with this probability, we'll go down this way. Otherwise, we stay in the susceptible state. Are we okay with that? Okay, ladies and gentlemen. How long do we remain in the exposed state? Yeah, exactly. So the latent period, and so we go main dot latency period. Maybe it should be called latent period. Okay, how long do we remain in the infective state? Does anyone remember? Infectious period, I think. Main dot, I think I called it duration of infectiousness. Oh, wait a minute. We have to be careful. You notice it's putting years next to this. We should make sure, I'm not sure if it will automatically convert, so I'm just going to say days.
It treats it as the last one.
Treats it as years?
If your parameter is 1 minute,
yeah,
and you're putting it into a rate where it says seconds,
yeah,
you treat it as 1 second.
Yeah, okay, right.
Does that make sense?
Yeah, so it treats, it overrides, yeah, exactly, which is
somewhat bothersome.
It's bothersome.
Yeah.
So near yet so far to greatness.
Right.
Yeah. Okay. Ladies and gentlemen. So let's, and I'll do one final one. Duration of immunity, sort of waning immunity. Okay. That's that final transition here, and that's going to be based on a timeout of what? main dot duration of immunity. Okay, so I'd like to go through these one by one, ladies and gentlemen, so you can make sure you've got the correct values. And then we'll complete the example. Okay, ladies and gentlemen, I'm going to go from the top. We have susceptible going to exposed in two ways. One way, which is a definite pathway, which we need to sort of guarantee that someone's initially infected, is this one here. And this one is a force infection pathway, this one here. And this is triggered by a message on a particular message, force infection. Are we okay with that? That's what triggers that. We need that to go directly to exposed because we want to force the initial person to be infected. Are we okay? Are we okay? Okay, ladies and gentlemen. For this one here, this is a message transition. It's triggered on a particular message, and the message is messages.exposed. Now, the default transition is someone stays uninfected. But if with a certain probability as given by, and this is the condition transition, certain probability as given by transmission probability in main, they will transition on to exposed. Does that make sense? We're going to flip a coin. They're exposed, and they have a certain chance, given that exposure, of contracting it if they're susceptible. And if they don't contract it, they remain susceptible. If they do contract it, they enter a latency phase. Now, after a certain latency, please make sure this is in days, right? Days here for this timeout given by latency period in days. Are we okay with that? This guy here, latency period is in days. Latency period, okay? Recovering. The timeout here is duration of infectiousness, and it's in days. And then, finally, last but not least, waning immunity, timeout based on duration of immunity in days. Are we okay with this? Okay, ladies and gentlemen, what do we need to complete this? There's not many steps at all. What do we need? We need a transition for what? Indeed, for contact, right? With uninfected for successive exposure. So there's going to be a contact transition. At what rate is that going to occur? Contact transition, show the name. And it's going to occur at a rate as given by what? Contact rate. And I think we said per day rate is how we specified it. Is that right, Kurt? In Maine? Pretty sure that's correct. We said contact rate was a per day rate. Okay? There's a contact rate. Are we okay? Okay? And what do we have to do every time that contact occurs? What's the action? Okay, yeah. And who we do send to what? Which one of these? Does anyone remember? Random connected. And what's the message we send? Messages.exposed. That's the message we send. Okay. Ladies and gentlemen, we're just about done with all the logic for this. We've got a teeny bit of a visual visual depiction. What's the final crowning thing we have to do? We need to start someone infected, right? Somebody somewhere has to start infected. Are we okay with that? Yeah? Okay. Ladies and gentlemen, so may I suggest so does anyone want me to show something here? Anyone want me to look more? Okay, if not, let's go to main. Let's go down main. We're just about done with this. Within 5 minutes we'll be done with constructing this. Let's go to agent. Let's create an event. In this event, ladies and gentlemen, will be initial infection event. Is that okay? It's in main. This is going to go out on one time at the beginning time. You can actually do this in what's called the startup code, but it's more clear if you do it in an event that goes off the beginning time, because you see the evidence event, you can name it accordingly. So we haven't changed anything from the defaults here. This is what it needs to do. It is going to need to choose a random city, and it's going to infect a person in that random city. Is that okay? I'm going to start one person in some city. How can we find a random city, folks? We're in main. How can we find it? This code is running in main. How can we find it? This dot cities dot what? Begins with an R, ends with an M. Random. Cities, okay, this will find a city, and then we can say deliver to random agent inside. We want to find that city. We want to get the no, we want to find that city. That's correct. Deliver to random agent inside. And what do we want to deliver as the message? Which message? We have two messages. Which one do we want to deliver? Force infection. Messages dot force infection. Are we okay with that? Okay. Oh, it's complaining about contact rate. Oh, it should be main.contact rate, sorry. Main.contact rate, sorry. Okay? Okay, ladies and gentlemen. So let me go back. Initial infection event occurs once. So let's go over what this means. Okay, I get my cities. I pick randomly from the cities. I pick one city. This gives me back a random reference to a random city. I ask that city, deliver to one of the agents inside of you. Who are the agents inside of cities? People. Force infection message. Are we okay with that? Okay. Now, ladies and gentlemen, okay, who needs to look at something more? So we go, we get the cities, we pick a random city, and we tell that random city, deliver to a random agent inside you, which is a person, the force infection message. Does that make sense? Ladies and gentlemen, this model should work as we speak, but it will not be visible. What do we need to make it visible? What do we need to see the colors changing? Yeah, let's go do that. Now we could also plot some graphs and so on, but let's go to this thing here. We need a variable, okay? Okay? Okay, I recognize it's past 5 o'clock, but we're just going to add in this color variable and quickly wrap this up. Win one for the Gipper. Okay? Okay, so drag it in there, and its name is color, spelt in an American fashion. Okay? And what sort of type is this? You've done this many times before. What sort of type? It's an other, and it's capital C color. Any logic has a set of mechanisms you use again and again and again. It's not overwhelming, it's just you got to sort of be comfortable with that set. Okay, so this is capital C color. It's going to start as black. Okay? And now what are we going to do to make it color? We're going to do two major sets of things. First, what do we have to do?
Make the person feel.
Good, good. We might as well start with that. That has this sort of dramatic unity to it. Okay? So we're going to go to person. We're going to go to presentation. And here's shape body. And where do we do this in shape body? Where do we go?
Go to presentation in person.
Good. Presentation in person. This is over here in projects. And we could select shape body. And where do we go within shape body?
Fill color.
Fill color. Okay? And what will the fill color be? What will we use as the fill color? Color, the variable. Oh, I don't know why this just flipped. Okay, fine. Color. Are we okay with that? Okay, and now what do we have to do to complete the thought? To complete the logical chunk of work? What do we need to do? In the state charts, we need to do what to color? Yeah, we need to assign it at each point, right? Now, by convention, I'm going to color these accordingly. Green for susceptible. Yellow for exposed. For infective, I pick red. And for recovered, ladies and gentlemen, as for men in that first example, I pick gray. Okay, where's my gray? Gray, okay. Ladies and gentlemen, susceptible equals, we have color equals green. Do I need a semicolon or not? I do, because I'm telling it, do this. It's not asking for a value. I'm saying, make this happen. Make it happen.
Do
Right?
this, don't do that.
Yeah.
Can't you read the sign?
Yeah. For exposed, I'm going to set it to yellow with a semicolon indeed. For infective, I'm going to set color equals red with a semicolon.
And we don't need two equal signs for these?
No, because 2 equals is, you're asking a question, is this equal to that? You're asking it to tell you not whether they're equal. So it's kind of, conceptually it's like saying is A greater than B. You're testing are they equal or not. Here we're actually saying make color equal to this, like change it. And so we don't actually need to do that. Double equals is used to ask, are they equal? Is the color gray? Okay? Does that make sense? Yeah. Okay, so ladies and gentlemen, for me it builds. Who needs Krugerian help? Krugerian consult. Okay? Okay. Okay, I'm not sure, is anyone starting infected? But oh, what just happened? Oh, maybe it's dying out. Okay, oh.
And it died out.
Did it die out?
Yeah.
Oh, it died out. They lost immunity. They were newly waned, didn't it? Okay, ladies and gentlemen. Okay, so we're going to need to fob some of those settings, which is why it was advantageous for us to define them as parameters. So now we can define these settings. Okay, ladies and gentlemen, I'd like to to fob these settings. So this will be baseline, This will be the baseline that we've got right now. And I'd like to add in so when I run this baseline, what I actually see is, an outbreak occurring and then it recovers. Something is wrong though. It's recovering so quickly, Kurt. It's getting back. It's almost as if duration of immunity is too short or something like that. Duration of immunity is 270 days. I don't know why it's getting back. This is a timeout of 270 days, but watch this. Okay? And it recovers. Did you see that, Kurt?
Yeah, within 1 or 2 time steps.
Within 1 or 2 time steps. Okay? So like right here, all these people have been infected, and now it recovers. Okay, something is going on here.
Years.
What's the,
Nate, your time is years.
for what?
Your model time is years.
Yes, but that shouldn't matter for these.
So it's 270 days,
Yes?
which is less than 1 year. So within 1 time step, they're all becoming.
Oh, of course. Yeah, right. So it's just how it's showing it, it's within a year.
It's within 1 time step.
Yeah, exactly, which is a year. So it's simulating year by year by year. Quite right. Okay, so that's interesting. Let's go create a new experiment. So that kind of makes sense. People aren't moving that quickly, so they're not bringing it from one to the other. Let's do a long latency and infection duration. Okay? Long latency and infection duration. Okay?
What was that?
I thought I was complaining about the long days.
Okay, so let's make the latency period, ladies and gentlemen, not 30 days. Make it 30 days rather than 3. Make it, 45. Say 30 days. That's fine. And the duration of infectiousness also 30 days. Okay? But that's not going to cut it. What I think is going on is that we have people moving so infrequently that they're actually not moving it from one population to another. So if we confine this duration of infectiousness 30 days, latency period at 30 days, ladies and gentlemen, here we are. Okay. Oh, look at that. Oh my gosh. Did you see that? Do you see that?
That is so cool.
Okay, let's be clear about what's going on. It's starting in 1, but then what's happening? It's spreading. And why does it spread? People moving. People are bringing it with them. Of course, it'll be even more pronounced if they were moving with higher likelihood based if anyone around them had gotten sick. And that could be readily done. You could have, oh, that would be cool. I'm not sure. Oh man. Well, okay. They might move out of a city if measles is raging around them or something like that, and move their kids away from a region. Although it's unlikely. But if H1N1 or something, if SARS, maybe they'll move to a further place. The point is that right now we have this migration event going off at a fixed rate, but we could have it go off more frequently if they were in fact recently exposed or knew others that were exposed. That wouldn't be a hard thing to put into place, actually. Quite easy. If we had another half hour, that could be readily done. Okay, now we have people moving between cities, and more than that, we have people recovering after some period of time such that they're susceptible again, and then it can spread again between cities, right? So here we have a meta-population model. We have several populations. There's movement of individuals between cities, and those individuals who move sometimes bring infection. What we should really do is make this rate of migration a parameter in Maine, because that's a key parameter, the rate of migration. So let's go drag in a parameter to Maine called migration rate. What sort of parameter will it be? A rate parameter, right? A rate parameter. And what will its time units be? We'll make it per year rate parameter. By default, it will be 0.1. People move once every 10 years or so. What do you think? Once every 10 years? And then, so we added a parameter to Maine called migration rate. We made it a rate parameter on a per year basis with a value of 0.1. And now we need to make that their actual migration rate. So how are we going to do that? Where do we go? Whither do we go? Back to person, migration event, and we make this a rate. Notice I could have done this migration with a state chart. That would have been another option. Either one, there are ways to make it have a variable rate, like if a person has higher risk perception, they're more likely to leave if they've had a history of exposure or what have you. Here, though, we'll make this depend on main.migration rate, right? Migration rate. And this will be a per year rate. Okay, ladies and gentlemen, per year rate. So now we can change that. I would suggest, ladies and gentlemen, that we ask the question, for the baseline settings for parameters, how frequently would they have to move for the infection to catch there? So I would say let's create a new experiment, and this will be baseline, or say higher migration. Okay? How high would it need to be to spread the infection? Right now it's 0.1 per year. Let's suppose it were, so that's once every 10 years on average someone moves. Let's suppose it were once every 5 years on average. Would we get the infection spreading? It looks like not. It looks like the infection even then does not spread. It dies out. What if it were once every 2 years? In other words, a migration rate of 0.5, ladies and gentlemen. What would it happen then? Okay. The threshold was crossed. Do you see that? Now we're getting spread across multiple cities. Although now it looks like it's died out. So it can run for a while. After a while, it dies out. Okay. Yeah. Okay. Ladies and gentlemen, how far does it have to be? You know, if it's every if it's every 3 years, for example, is it enough to? Yes, every 3 years is even enough to spread it round, at least for a couple. Okay. Meta-population model. I know it's been a challenging example, a lot of details here, but let's take stock of what we've got, because it's considerable in its virtues. We have Maine. We have cities within Maine. We have a hierarchical structure. We have people, cities, the global environment. These multiple cities each have an articulated population with its own networks. The cities themselves are arranged in networks. We've only tapped a tiny bit in having people move to a neighboring city. Within a city, it has its own network structure. The network among cities is distance-based. The network amongst people within a city, by contrast, well, it's also distance-based, but localized within that city. We could have it be scale-free within a city if we wanted to. That would be another option. Then we additionally have, within this model, movement from city to city, by which an individual who is in whatever infection status moves to another city with a certain hazard rate. And that individual can thereby bring new infection with them and spread the infection in another city. Were there time now? And there isn't, but were there time, we could go add graphs very readily. You know how to do that. You know how to add time plots. We could record, if we were to do so, if we wanted to do so, we could record how many times a given individual has gotten infected, the count of times, so we can know something about their history. And for example, put up a histogram of that. We could look at the fraction of infectivity in different cities, how the burden varied between these cities. We could examine in a systematic way how migration rate ends up influencing the burden of infection as compared to, say, transmission probability or network structure. So there's lots of things we could do with the model, and although it took some time to assemble, it took no more than an hour and a half. It's a testament to what you can do with a modest amount of resources to explore some pretty interesting dynamics which have some relevance to real-world circumstances, in the sense you have migration and carrying of infection, etc. So I hope that's been an interesting example. It's also shown us, some aspects of how migration works, particularly moving between populations. In this case, populations encapsulated within cities. A model like this, the statistics from it, which can be readily computed on a per-city basis or a global basis, could be further compared against hierarchical linear models or other sorts of multi-level modeling from a biostatistical perspective. And that could also lend some insights, because of the hierarchical structure here might mirror hierarchical structures in contexts where data is collected empirically. So there's lots of opportunities for models like this that are nested hierarchical to lend some insights. And this model, while modest, has some important potential associated with it. Okay, so it's 5:30. I've kept you at the end of a very busy day, and I want to thank you for your patience. Tomorrow we'll go on to hit more hybrid models. We'll see more aspects of hybridization. We'll also start to introduce some aspects of calibration and sensitivity analysis to see how those are conducted. Perhaps tomorrow. Some of that may wait till Friday. And we may additionally take a look at some other strategies for combining system dynamics models on the one hand with agent-based models on the other, particularly immunoepidemiological models where you simulate, say, within a person or an animal, their immune system status and how it affects the spread of infection in the population, and also models where system dynamics is used to represent most of the population in kind of a coarse-grained way, a rough and ready way, because it's not individuals at risk, but where certain segments of the population, people at certain risk, animals who are high-risk animals or have animals with a certain history, those will be represented with an agent-based model. So you have this kind of division where you have a coarse-grained representation for areas you're not too concerned about, you want to abstract away from the details, and the power to zoom in on areas where you care more about the details. So we'll probably be seeing that some tomorrow in our hybrid models. Okay? So that's all for today. Thank you for your patience and your stamina. I'm very impressed, and I believe Kurt has also commented how impressed he is with how much people are taking in here. This is not easy stuff, and I'm so impressed with how much you followed it. I will post the models, and I'll post the video, and I will look forward to seeing you tomorrow morning. Tomorrow we'll be sure to have Kurt and myself, as today, available for consults on projects. We had some good discussions over lunch, but we can also, please be sure to take Kurt during the day if you want to take him aside and discuss things with him out of this room so you can have less distraction. So thanks so much. I appreciate everything, and we'll see you tomorrow morning.